Okay, thank you. Let's move on from let's move on from ring theory and ideals. And whoever wants to can continue chapter 1 on their own and do more questions and exercises. Let's move on to chapter 2. Chapter 2 talks about module theory and many other very fundamental and important things in commutative algebra. So to start, this chapter requires a background in group theory, which we will not define. We'll just assume everybody knows some things about groups, abelian groups, etc. So starts off, so let A be a ring, and let's say an A module is an abelian group. I'll say about an A module, I'll call it, let's say M is an abelian group. So it's an abelian group M such that there is a map, I'll say A cross M to M. So usually we denote this map like this. So this multiplication just means you just define an operation from the ring A on M, and you end up back in M, such that for all A and B and A and X and Y and M, we have A times X plus Y. This distributes naturally. We have A plus B times X. This also distributes naturally. And then we have an associative property. And we also have this final property. So examples of modules could be, I didn't write many examples, but the natural example is let A be a ring. Then of course A is a module. It is an A module. Of course, this is the most natural module you could think of. Actually, you have seen many modules in the past. Let's say if A is a field, like we said from last chapter, let's say A could be the reals, A could be the complexes. You could say M being a V is a vector space. Or you can say a V is a complex vector space. Those are also modules. So if A is a field, not just a general ring, so every module over a field is called a vector space. There's also an interesting example. If A is integers, then M is an abelian group. So all abelian groups are modules if you consider A to be the ring, the integers itself. So one thing to note about the difference between vector spaces and modules is that, so when you have a vector space, the underlying ring is a field. So your elements are either 0 from the ring or invertible units. But that's not the case when you have just a general ring and a general module. So you have to be a little bit more careful. The theory is not that clean, I would say. It's more abstract. So let's define one more thing. Actually, how about I start this here? Maps between modules. So usually in math, when you have objects, you would like to describe maps between them. So again, let A be a ring. So M and N are A modules. let's say the first definition, so or maybe the second definition today is that a mapping, let's say F going from M to N is an A module morphism. A module morphism or A module homomorphism if for all, let's say, X and Y in M and R in A, we have F of X plus Y is F of X plus F of Y. So here I denote addition to be the operation of the module because addition is the most natural commutative operation, and so we always just say commutative operations are denoted by addition. So F of X plus Y should split up as F of X plus F of Y, and also one last thing, F of R times X should be F R times F of X. Okay, that's great. So in the case of if A is a field, then we have M comma N are vector spaces. Then these maps F, these A module morphisms, are just linear maps. So that's the case when A is a field. So a lot of the things we've seen in vector spaces in linear algebra are true for modules. So we see some generic structure inherited from vector spaces. There's also generic structure inherited from groups. So I will not talk much about this, but all the theory about submodules and quotient modules are the same. So if you have an A module M, say M is an A module. If you say M prime is a subgroup of M, then it naturally has an A module structure because of just the fact that M is also an A module. And also, if you have M prime is a subgroup of M, then we also have M mod M prime is an A module, with the operation being R times X plus M prime is R times X plus M prime. And you can go ahead and try to see why those this operation makes M mod M prime into A module. So this is all very nice. So we gave you some examples of modules. We gave you 2 examples of how to get more modules from modules you started with, submodules and quotient modules. So let's skip to one of the most important and most fundamental module in math. And this is not just for algebra, but this is fundamental in many branches of math: topology, number theory, etc. So what I mean is the tensor product. So Etienne McDonald talks a lot about the theorems and ideas of modules before he gets into the tensor product, but let's just skip to the tensor product. So if I say let A be a ring, and let's say M, N, and P are A modules, then I'll say definition. So I'm mapping, let's say, F from M cross N to P is A bilinear. Oops. If, first of all, F of, I'll say, M1 plus M2, N is F of M1, N is F of M2, N. And also F of R times M, comma N is R times F of M. And for all M1, M2, M, M are A, N, N, and also we have f of M and 1 plus N2 is f of M and 1 plus f of M and 2, and also M, comma, Rn is R times f of M. So this is what it means for of mapping to be a bilinear. So again, let M, comma, N be A modules. We will define a universal object into when we have an A bilinear mapping. So I will say that here we talk about the tensor product. So if we let M and N be A modules, I will say there exists a pair, I'll say T and G, such that I'm sorry. Yeah, and a bilinear mapping, I'll say G goes from M cross N to T such that, so this is where the universal object is defined, such that given any A module, let's say P, and a bilinear pairing, I'll say F going from M cross N to P, there is a unique map. Sorry, unique A linear map. F prime going from T to P such that F equals F prime of G. So what you're trying to see is that you have a map M cross N to this P, so if you have this map F, then there's a map G to this tensor product I'll call T, such that you can make this new map F prime, such that there is a commutative diagram. So again, F prime of G is F. So we will try to construct T. So how do you do that? So the uniqueness aspect is something you can try to find on your own. I'm sorry, there exists we'll say a unique pair. So how do we actually construct this T? So how do you actually construct T? So let's say C is the free A module generated by all elements of M cross N. In other words, I'll say C is the set of all formal linear combinations of elements of the form A times M comma N. So A is in A, M is in M, N is in N. So all formal combinations, all formal linear combinations of elements of this form, that's going to be C. And now let D be the submodule of C generated by all elements of C of the form, say, x plus x prime y is the same as, this is the same as x comma y minus x prime comma y. Or of the form x comma y plus y prime is x, keep saying equals, minus x comma y minus x comma y prime. Or all elements of the form, if I have r times x comma y, it's the same thing as, how about I say, it's the same thing, but how about I say r times x comma y minus r times x, y minus x comma r times y. So C is the formal set of formal linear combinations of elements of this form up here. D is a submodule of C generated by all elements of this form. So T is their quotient map, quotient module. I made a small mistake. Sorry. This should be, it should be, I think, r times x comma y minus rx y and r x comma y minus x comma r times y. It's probably the same thing, but just to be clear. Okay, so T is this quotient module, and let's say G going from M cross N to T is the obvious mapping. All elements of the form get sent to M comma N plus D. So this T comma G is the desired object. And you can prove on your own why there is a unique, so if you have two such objects, T and T prime, G and G prime, why there is a unique isomorphism of T and T prime. So from now on, it's ugly to always call T to be C mod D. From now on, we denote each basis element of T. I'll call this M tensor N mod A as, let's say, M tensor A N. Or So from now on, no more C, no more D, it's M tensor N. And so note that due to this reduction, we have M plus N prime. Actually, M plus N prime, we'll call this tensor N, is the same as M tensor N plus M tensor, M prime tensor N. Also, we have M tensor N plus N prime is also M tensor N plus M tensor N prime. And then we have the third statement is that if you have R times M tensor N, that's the same as M tensor R times N, and that's the same thing as R times M tensor N. Okay, so this is a nice way to kind of reduce all of these operations here into a very big, important module of the tensor product. So moving on, there's one last thing that I'd like to say before we get into some questions, which is the tensor product also is an application in linear algebra. So if you have two vector spaces V and W, you can actually take their tensor product, be tensor W, in the exact same way we did above, because at the end of the day, vector spaces are modules. You can take their tensor product. The dimension of the tensor product of two vector spaces is their product if the dimensions you started off with are finite. Okay, so the first proposition for today I will cite as proposition 2.14 from the textbook is that tensor products behave nicely like this. Actually, how about I say let M, N, and P be A modules, then there are unique isomorphisms. The first one being M tensor N is isomorphic to N tensor M. You would not think that the tensor product is not commutative. It should be commutative. It only makes sense. So there you go. And then number two is that M tensor N tensor P is N tensor P. Of course, the tensor product should be associative. So if you have the direct sum, it should behave like M tensor P, M N tensor P. So the tensor product and direct sum behave like multiplication and addition. Multiplication is distributive over addition. And the fourth one, I said, should look like this. So let's prove the first one. So how do we prove M tensor N is isomorphic to N tensor M prime? Well, the natural thing to do is say, if I want to prove an isomorphism, I should just be able to see where the basis elements get mapped to. Why can't I just say M tensor N maps to N tensor M, and then prove it's a bijection and it's a homomorphism? That's perfectly fine. That's perfectly fine. But you should make sure that this mapping, this operation, is in fact well defined. To do that, let's actually prove, let's say that M cross N gets mapped to N tensor M. So I will not go through the whole details, but I will in fact say that this is an A bilinear mapping. So the natural mapping from M cross N to N tensor M, mapping M comma N to N tensor M, is in fact A bilinear. This follows precisely from the construction of the tensor product. And so there is a mapping, I'll say phi prime, from M hat and M tensor N to N tensor M. How about I write it this way? Phi prime, and then I have, remember, I have the G, and here I have the phi. This should be commutative. So if you have M comma N maps to M tensor N, and then this maps this way, this goes to N tensor M, it only makes sense that phi prime of M tensor N equals N tensor M. So we have proved that this map is well defined. So using this universal mapping property from the tensor product, we are able to prove that this mapping that we expect to work is in fact well-defined. And so the only way you can prove that this mapping is well-defined that I can think of is to actually go back to the definition of the tensor product, like we did here. What I'll say, the only way we can prove such a mapping is well-defined is if we go back to the construction of the tensor product this way. So this shows you that the mapping is well-defined. That is the hardest part of this question, and so proving injectivity and surjectivity is not that much harder. So let's move on. So the one last thing I also would like to note is that exercise 2.15 in Atiyah McDonald is extremely important, which I will now prove. It's a very strange idea, but when I've been doing the questions from the back of the textbook, this idea has come up a lot. And for some of the questions, it is the only way to solve some of the questions. So if A and B are rings, M is an A module, P is a B module, and N is both an A module and a B module, then how can we relate the two? Then I will say that M tensor A N is a B module by the fact that you can take the dot product and do this. This has a B module structure from that. We have that N tensor BP is an A module. From this structure. And finally, we have that M tensor N tensor P is isomorphic to M tensor A and tensor B P. So it shows you that even though you have two different rings, you can relate the tensor products of different rings together. It's very, very strange, in my opinion. But it is very powerful because I've been able to use it to solve many of the questions from the textbooks that I've tried to do. And then this is very important, but the final thing I will say are flat A modules. So I will talk more about this next week, but I will just give the definition right now because it's a nice definition. Let A be a ring, M an A module. We'll say that M is a flat A module, or we can just say M is flat if whenever we have two modules N and P are related to by F, with F injective, then we have that M tensor N and M tensor P are related to by this map, mapping M tensor N to M cross F of N. This map, 1M tensor F, is not necessarily injected, but if M is flat, than it is. Okay, so here I gave you a lot of definitions, and it's very abstract. It's very hard to understand what's going on because I only gave you definitions so far. How about we try and do some questions from the textbook? So everything good so far, Gunhee?
Yeah, very good. I'm just thinking about the terminology at this point. Like even though we use the terminology, say tensor product between two modules, but in fact we don't care about the multiplication. Seems like product is relevant to the multiplication, right? But I know that this is somehow silly and stupid, but
so I'm not sure precisely where the terminology came from, but if you remember up here, so here it does look like this tensor. If you think of this as multiplication, and if you think of this direct sum as addition,
yeah, sort of, yeah, sort of.
It does look like, yeah. Certainly, I'm sure there's more relationship between tensor product and multiplication than just that, because of course, like you saw, the dimension of the tensor product of two vector spaces is their product. So maybe I'll study some more and have a better answer to your question.
Yeah, thanks.
Okay, so let's try easier questions to harder questions. So let's say M and N be coprime integers. I will prove that Z mod MZ tensor product Z mod NZ is 0. So how would you do something like that? So just a minute. So let's say you have this case. So I don't know what this tensor product looks like, but I do know that it is generated elements of the form A tensor B, where A is in Z mod MZ and B is in Z mod NZ. So if I prove each element of this form is 0, then I'm done, right? So how about we say M tensor B is the same thing as 1 times A tensor B. There's nothing wrong with that. That's perfectly correct. But when two numbers are coprime, there is a special relationship with the number 1. I will say that 1 is equal to X times M plus Y times N for some, X, Y, in Z, right? So instead of saying A tensor B, that's the same as 1 times A tensor B. That's the same thing as, like what I said, X times M plus Y times N times A tensor B. And so by the construction of the tensor product, this is actually equal to X times M plus Y times N times A tensor B. So this is equal to, let's say, X times M times A plus Y times N times A tensor B. So remember that this A is in Z mod MZ. And so if you multiply something by M, it becomes 0. So this is actually just equal to Y times N times A tensor B. Okay, so that's fine. So we reduced it a little bit. We made a step forward. This is good. This N is an integer. So let's pull it out. This is still equal to y times a cross product, tensor product b. There's nothing wrong with that. That equality is because of the construction of the tensor product. Great. Now this is equal to y times a tensor product n times b. Okay, so again, like I said above here, b is an n, z mod nz, and so if you multiply anything by by n in z mod nz, you get 0. So this is y times a tensor product 0. So I claim this is 0. So y times a tensor product 0 is the same as y times a tensor product 0 plus 0. So by the construction of the tensor product, this is the same thing as this. Sums get broken up. Sums in each component get broken up. But then we have here and here are the same thing. So we have y times a tensor product 0 is the same thing as the thing we started with. This is 0, and we're done. Okay? So that is the first question that we solved from the back of the book. So let's move on to, let's do number 2. A be a ring, I an ideal, like we talked about in chapter 1. Let's say M is an A module. Show that A mod I tensor product M is isomorphic to M mod IM, where IM is a set of all formal linear combinations of elements of the form, let's say I times M, where let's say I is in the ideal I and M is in the module M. Okay, so how do we do this? So again, you want to say that the natural thing to do is take each basis element like this and map it like this. So you have an A here, you have the M here, you somehow have to relate them and then end up in M. So if you multiply A by M, you should get an M, and then if you add IM, you back in M mod IM. So again, this is difficult to see if this is a well-defined map. So what you have to do is go back to the construction of the tensor product. Okay, so let's take this map. Let's take this map F. So it's not A mod I tensor M, it's A mod I cross M, direct product. So let's do this map. Okay, so let's actually prove it is bilinear. So if I say that A this is equal to F of A M1 plus I comma M, this is the same thing as A1 plus A2 times M plus IM. That's the same thing as A1 times M plus A2 times m plus im. This is a1 times m plus im plus a2 times m plus im. That's the same thing as f of a1 plus I m plus f of a2 plus I m, etc., etc. F of r times a plus I m is the same as f of r times a plus I m is r times a times m plus I m, which is the same thing as r times a times m plus I m, which is r times f plus a plus I, comma. So this is bilinearity in one component. You can prove the bilinearity in the other component. It's very, very technical. So what I'm trying to show is that it is in fact I'm sorry, what was it? This is in fact commutative. And the map I'll call phi, phi, behaves well defined. Like I would, I'm sorry. This is F, this is a G that we defined earlier. It is commutative and everything is well defined. So what is left to prove is that, so this is, what we have is that I mod IM is the universal object. That factors through the tensor product. So we can in fact say that mod I tensor M is isomorphic to M mod IM. Okay, so I'm sorry. I have to prove one last thing. I'm looking at my notes. I have to prove that.
So you'd like to prove that that is the universal object. So
that is it, yes. Okay, so this is one half of it. So if I say that let n be an A module with, let's say, phi, I'll call it psi, and is bilinear, then there is a unique mapping. There's a bilinear map. Try to look at my notes again.
Yeah, I think you can maybe start from here next time.
Yeah, I think so. So bilinear, and then wait. Yeah, I think it's best to restart here because I think I'm soon.
It seems good exercise for
out of time.
Let me think about it.
Yes. Okay. One half finished. Yeah. Okay. So yes, for next week, let's finish number 2, and then also we will talk about. Okay. Yeah. I'm sorry.
Yeah. What's the next?
So next week we will finish this question, actually prove it is the universal object, and then talk about Nakayama's lemma and so exact sequences and more exercises from flat modules.
Yeah.
So yeah, okay, it's good to be back. Took a short break.